for you. Can you read things?
Yes, it's great.
I don't know how big your monitor is. Okay. So that's some data with the wide field imager taken in La Silla in Chile. So that's similar to the wide field imager in La Palma. The only difference is there's 8 detectors instead of 4, but the principle is the same. And so that's just data from one night. And you see that the setup is basically the same as for what you probably did for version 2.
Yep.
So you have a directory with the biases, and then 3 directories for the flats, taking PVR filters, and the same for the science exposures. And in the new version of Theli, you can enter several directories for these calibrators in the science. So you can check in all your H alpha and the on band and off band, and then you need to provide the same number of science exposures directories. So the biases, if you only enter one bias directory, then that would be applied to all of them. If you wanted a separate bias directory for each science directories, you would need to enter a corresponding number of entries.
Okay, so it's not matching the flat by filter, it's just
no, it does
matching
not,
it by order.
It does not trust any header keywords. So you still need to make sure about that. So in your case, you would have flat H alpha and flat R, and then NGC something H alpha and NGC something R band.
Yep.
That would be for one target. What I would do in your case is I would dump all exposures in one filter in one night, or actually in all night. Let me think. Yeah, I think what you can do is you just create 2 directories or 3.
Yeah, I think in this step I have like a target R and a target H alpha, everything in the same filter.
And yeah, and probably some target H alpha redshifted.
Yeah, exactly.
So I think that's the right way of doing it. So you create 3 flat fields in your 3 filters, and then you create 3 directories where you dump all the various filters across all nights. You just collect
across
everything.
All nights. Okay. Yeah, I haven't done that.
Just because the argument is that the flat field and the bias doesn't change across nights. Therefore, you don't need to keep things separate. At least that will simplify the first half of your processing. So you would do that. Now let me restore my setup here. Because then you only have like 3 entries here and there.
Yeah.
If you have like 20, these line fields are a bit short. What you can do is you can pull this thing out. Then you have more space, but then sometimes it happens that it doesn't. You can't anchor it again. That's a bug in the library that I'm using for this interface. Right now it doesn't. Somewhere there's a sweet spot. Let me start this again. Okay. So once you've done this setup, then you do this HG reformatting. That's basically correcting for nonlinearity over scan, and it adjusts the gain factors. You create your master bias and the flat fields, and then you apply everything to your science data. And it works sequentially through all the directories that you defined. The only thing that is important here is that you match if your order is flat R-band, flat H-alpha, flat redshifted H-alpha, the order needs to be the same for the science directories. Otherwise, they're not aligned correctly.
Yes, I noticed the naming convention is different, at least for for the files that you're creating from the version 2.
Yeah. Yeah, I'm trying to rename things to instrument name, then there's a filter name and then a timestamp. But you can turn it off if you, for whatever reason, you don't like it. You can up here in this configuration tab up here, you can remove this tick mark up here.
I see. Okay.
And then it just keeps the original file names.
And that's the date of the observation, right? Not the date of the.
That's the date of the observation.
Yeah. Okay.
It reads the timestamp in the header. So for in your case, I would recommend that you use this naming convention scheme because it makes it a little easier for you to associate the data. If something goes wrong because you've taken things across different nights.
That's true. You can separate it easily.
Just by looking at file names, then you know when stuff was taken instead of relying.
So I had this issue with when one of the nights, or even a couple of the nights, the telescope communication was breaking down between the camera. So some of them didn't have the right header information. So I was copying headers from one file to another.
Okay, so what header information was missing?
Like all of the WCS information. So then it would, the scamp wouldn't work down the line. So I had tried just copying RA and DEC from the primary.
That might not be enough.
It wasn't enough, yeah. So then I ended up just doing the whole thing, but I probably have the same time. I probably overcopied the time too.
Let me have a look in my source code. I'm catching most of these things and fall back to default values. I'm definitely writing the CT matrix.
Yeah, I tried to do it before it did the split it into individual frames.
If you know the RA deck or missing, you could do that. But
yeah, it didn't work though. At least just the RA deck didn't work. I put that sort of in the main header. I updated the RA and deck from like a neighboring image because they're only slightly shifted.
Yeah.
But there's something else that I was missing because Scamp didn't work on that. But
okay. Well, let's not worry about that for the moment.
Yeah.
I think the new version is more robust in this respect. Well, of course, if you're completely missing RA and deck, then you should try and provide it manually, like you said, on the raw data before you process it. And then if you run into a problem for it during astrometry, you can try and fix it individually.
Yeah.
I can show you how to do that.
Yeah, okay.
Okay, so once this is done, then you have all your files, and like with the old version, they're broken up into the individual chips. So in this case, they run from 1 to 8. This identifier string in the old version, I think it was OFC or something like that.
Yep.
For overscan corrected, flat fielded, and trimmed or something like that. I changed that, so P just means ran through the pre-processing step.
Okay.
And you don't need to really worry about that. Later on, once they're flat fielded, they get a little A. Okay, so in here, in this memory viewer, oh, all right, that's something I wanted to ask you. How much RAM do you have on your machine?
That's a good question. I'm running it on I'm going to try and run the rest of it on a virtual machine. I think I have 32 on my laptop, but I don't do you know a command line way to find that out?
Free.
What's that?
Free, just FREE.
Oh, so this says
are you on a Mac
62 gigs on this virtual machine.
Are you on a Mac or on a Linux box?
Linux.
Okay.
Yes, I have like 32 on my laptop, and then the machine I'm going to try and run this on, it has 62. That's what it says.
Your virtual machine has more memory than your laptop?
Yeah. I don't know what, I don't actually know what it's like a computing virtual machine that our ITS is setting up. Yeah, like
okay.
you know, 60, whatever, 64 terabytes of.
Okay, perfect. Then.
No,
nice. I meant memory. I meant physical memory, like RAM, not disk space.
Right. No, I'm just saying for this virtual machine, it's got way more. It's like I don't understand exactly how they're setting it up, but it's got like an 84 terabyte drive and the memory is 62 gigabytes.
Okay, perfect then. Good.
Yeah.
Yeah, then you certainly won't have a problem. So,
mm-hmm.
Because this new version, in the old version, it never kept anything in memory. It always did something, and then it wrote the result as a FITS file, and then it read it again and wrote it out. So it was very slow.
Okay.
And in the new version, it keeps everything in memory. Unless you run out of memory, it starts to write FITS files. To you, that is, you don't need to worry about, or you don't need to be concerned about this. The only thing you should not do is while you're processing something, you should not start moving FITS files around in the data tree. Because if you do that, then the software might expect the FITS file to be present because it couldn't keep the data in memory, and then it doesn't find anymore because you tried to move it out of the way because it was bad or something. Like in version 2, you could do that easily because basically what you saw on disk was the data model the software was working with.
Mm-hmm.
So at any point when there was no processing going on, you could move things forth and back or delete stuff. In the new version, you shouldn't do that anymore.
Okay.
Just saying. If you want to look at things, you can go into this memory viewer tab, and then there you see all the, first of all, up here.
So those are all in memory right now?
Yes.
Wow. Okay.
Or on disk. At the entire data tree you define here.
Mm-hmm.
And if you go into this memory viewer, you can select it up there, the various flat fields, biases, and so on. And you just click on things and you can look at them. There's some aliasing effect. Same for the science exposures. So, for example, this one, just click on it, and it's like DS9. If you do a left click in the image with your mouse button, you can measure distances, or with the right mouse button,
is this what is the thing you're using? Because I tried writing a GUI for doing the downstream H alpha reduction. I forgot
this GUI here.
Yeah.
This is it comes with the software. It comes with Theli. It's an internal FITS browser.
So you wrote it?
I wrote it.
Oh, okay. Oh, so, very nice.
And thanks. In this way, I can
one
access.
That like Space Telescope was doing, trying to replace DS9.
Ah, okay.
I can't remember what it's called right now, but Ginga. It's called Ginga. Maybe it's not Space Telescope.
I think I heard about that.
Yeah.
I just felt like the need to interface with the data. If I keep all the data in memory, then the user doesn't have a way of looking at it.
Yeah,
So
no, that's awesome.
you just click there, and if you want, you can go back in history. You can look at how did the image look like before you flat filled it, like the raw data. How does it look like after flat filling?
Oh, wow.
So you can go forth and back and study the effect of your calibrations on the data. And if the file is not in memory, then it will just read it from disk.
And you got that just by double clicking on the image, or how did you open that? Sorry, the display frame.
You just you either click on the columns which are blue, meaning it's in memory, or this data product exists, or you just click here on a single click on the name of the file.
That's very nice.
And yeah, so that's a very easy way for you to interface with the data. If later, okay, that's all I want to say about this right now. Down here, you can do a binned preview. Basically, that's it just pastes all the detectors together.
Nice.
Those are obviously wrong. I don't know why they're wrongly scaled. Oh, that's some very old wide field image. I need to look at them. That's probably just an artifact in how it measures the. Okay, ignore that. That's specific to this data. So you have an easy way to eyeball your data, and you can use these arrows up here to quickly navigate through your exposures.
Oh, that was just one. Okay, yeah.
So, for example, if one is really crap, if the tracking is bad, you would see it immediately.
Yeah.
And then you could reject them. You can also do that here. So when you click on an exposure up here, so that would be the first chip. You can change the frequency by which things are displayed here, and then click on the play button. And then it automatically cycles through all the exposures.
Wow.
And you can see if one is crap and flag it.
Yeah. So is there a way to remove it in this list, or
you just if there's an exposure you don't like, you just deactivate it here.
Wow.
And then, so that was.
This is really nice.
08.15.6 in R band. So if I go into R band, you see now there's this inactive directory.
Oh, that's cool.
And it has that image in there. And if you want to restore it, you just click it again. And then it disappeared from the inactive directory, and it's back in the where it used to be. Internally in the memory model, it just tells it to not use this exposure. And since I'm writing all of the exposures to drive as well, you can see that this is something you can turn off here in the settings. There's a flag, it's called store intermediate data, which here it says always. If you have a lot of memory, you can say only if necessary. That would save you all the I/O onto the drive.
Great.
But in your case, I recommend that you leave that on always, because if something goes wrong, you don't lose it.
Yeah.
You have it on disk, and you can just resume where you left off.
Okay. Right, and then for the parallel computing, do you have to set that automatically, or does it?
You crank it up to as many CPUs as you want.
Okay.
So I don't think you'll profit from more than what you said. You have like 5 exposures. you probably don't see a big gain if you have more than. Wait, no, you're wrong. I'm wrong. Normally, I would say it doesn't make much sense to use more CPUs than you have detectors.
Okay.
But in version 3, some of the parallelization is done not based on the detectors, but based on the number of exposures you have. So if you have like 50 exposures, then you would profit from,
Okay.
you would benefit from using 50 CPUs. But I think your data set is not gigantic. So
yeah,
just 8 or 16 or whatever. And
yeah.
in the worst case, some CPUs are just idling and they're not being used. I think the maximum number it comes up with is, the default number it comes up with is the maximum number of CPUs that are available. So you would need to look at what your user policy is for that virtual machine.
I think they're all mine, actually. So
after all, you're okay.
yeah.
Not that you're a share or that you take away all the CPUs from someone else. And
I don't think so. I think
make
that
someone
they somehow
unhappy.
rationed it when they set it up.
Ah, okay.
But I'll find out, I guess, right?
Then yeah, someone will yell at
I don't
you.
think a lot of people are using it right now. So
Okay. No, then just check. I don't know how it is with the virtual machines, but it should be able to detect the number of CPUs it can use, and that should be the
yeah,
number
I'm just
that
opening it right now.
ends up here.
Yeah. Okay.
Okay. All right. So let me go on. So the next two things you need to do is create the weight maps, the global weight maps and the individual weight maps. It's the same as in version 2. I think you're familiar. Are you familiar with them? Yeah.
Yep.
Then there's nothing really to say about it. You just run it. Next thing is you have to create the source catalogs. So that's again the same.
So here I would have separated the targets, but I was debating this because because Scamp can do the separation. Basically, you can run Scamp on everything at once.
In principle, yes, but not the way I'm using it.
Okay.
The reason for this is that Scamp allowed some flexibility in terms of what you just mentioned, and also the catalogs it's been using. But until very recently, I thought that was actually very limiting. And that's why in Theli, I'm creating the catalogs, even the reference catalogs Scamp is using. I do not let Scamp download.
Oh, okay. Okay. I was wondering why that was different. Yeah.
That's I just saw that in the generic case, Scamp is not flexible enough. If you have a field with extremely high stellar density, for example, Scamp might download way too many sources and then never converge to the true solution. So you have control over this, and it's now also automatized. So what you would do is you would click this separate target groups button,
right?
Which I can do here. And in this case, it just recognizes that there's only a single target in the science directories. So it leaves them unchanged.
Okay.
If there were more, then you would now, here you would have...
yeah, like the science one too. So the same as it did in...
Yeah, I think it would be underscore set 1, set 2, set 3. And I don't remember my own source code correctly, but I think that these fields here are then also automatically updated. So you would get a very long,
oh really,
a very long list of strings in here which you wouldn't be able to display.
Okay.
But then you could just continue normally, create catalogs, do your astrometry, sky subtraction, and coaddition, and it would step through each.
And it would do for each target.
It would do it for each target. It would download the new reference catalogs, everything. So in principle, at least that's the idea, everything is automatic. If you have a very large number of targets, chances are that one of them, something is going to fail for one of them.
Yeah.
There's dramatic solution because you hardly detect any sources in your Halpha image, for example. And then it would be difficult for you to trace steps. Where exactly did it fail? How do I continue?
Right.
Now, not having done myself very much, I can't really, wouldn't even know what. I don't know what could happen. So, in what you could do is you could do this, separate your target groups, and maybe just when you try this, just use one knight instead of all 10 knights.
Yeah.
Just to limit things a little bit.
Yeah.
Or maybe even manually remove.
Some
only
from the
keep
list or
3
something.
targets of a knight. Start with a small data set and see how it works. But apart from that, in principle, it should do everything automatically.
Okay.
So catalogs, I implemented the Gaia release 3, the early data release, which is really nice. So let's run
No,
that.
I was wondering, do you have to, I wasn't sure when I was trying this the other day if I had to get the catalog, because there's like a get, like
it's doing it. Yeah, it's doing it automatically now.
Okay.
You can,
because there is a little button to click when you opened up that menu, right?
Yeah.
But you don't have
you
to.
don't have, you don't, no, you don't have to. You can do it, so you see how many sources it detects. Then you can fine tune your magnitude threshold if you think it's not enough. But you don't have to. So when you create the source catalogs, you see how many detections are made in each exposure. That gives you a rough idea of whether your field is crowded or not. And then
where did you set is there a way to set the mag limit on that?
For the ref, wait, right now it's
for the reference catalog.
Yeah, it's down here.
Oh, okay.
But usually in your case, if it's like external galaxies, don't set a magnitude limit.
Don't do it. Okay.
You're not, these are not crowded fields unless you observe
some that's true.
galaxy behind them. Okay, so just don't impose a magnitude limit. And I think unless you observe it, the North Galactic Pole where the source density is extremely low, I think you're fine with Gaia 3. If not, if you want deeper source density, you can use Pan-STARRS or SDSS.
Okay.
Both of which are at least calibrated against Gaia DR1. So it's still reasonable astrometry.
Okay.
Yeah, the nice thing with Gaia is previously in version 2 for multi-chip cameras, you had to use this instrument and fixed focal plane parameters for SCAMP. You do not need to do that anymore. This is because the Gaia basically does not have any astrometric errors that you can resolve with your instrument or with the wide field imager. So you can just do it on a exposure by exposure level. It works amazingly well. I was really surprised by that.
Wait, I guess I'm not sure I understand what the difference is then.
The difference is if you do previously with by setting the stability type to instrument, you force the distortion to be identical across all exposures.
Gotcha. Okay.
And the fixed focal plane, what that does is SCAMP does it attempts a first matching, So it knows where the detectors are on the sky, and then it needs at least 5 dither exposures, and then it calculates a median relative positioning between the detectors. So it fixes the shifts and the rotations.
Okay, so I was wondering if, like, in your instrument setup files, you were giving it the alignment of the CCDs.
Yes, there is. That's a fallback in the old version.
Okay.
You could use in the old version. You could use this. In version 3, I call it use prior. In the old version, I called it like, I don't remember what I called it. You could load a default a file which had the default reference positions. The problem here is that now our instruments are used for a decade or even longer, and they're cryocycled, they're taken apart, they're being put together, they age, the epoxy with the detectors outgasses, so detectors drift over time.
Yeah.
Scales of pixels, but enough to screw your astrometry. So
Okay.
the best is always that you determine the astrometry based on your data set. And before Gaia, you had to use dithered exposures with ideally lots of stars in it to measure it accurately.
Yeah.
The relative positioning, and then you tell SCAMP, okay, compute the median relative positioning between detectors, and then always use that. This is what this fixed focal plane setting does. But with Gaia, you don't need that anymore, because Gaia is so precise and accurate that you can just do it on an exposure by exposure level independently, unless you have extremely low number of sources, which maybe you would have with infrared detectors, which have a smaller field of view and the exposure time is only 10 seconds.
Right.
Then if you observe something in the North Galactic Pole, then you have 3 stars in there. That's then not enough. Then you can use this fixed focal plane. But for the INT, even in the H-alpha data set, I think you probably won't have that problem. So I recommend you use this exposure loose setting and ignore any prior information. You need to use SCAMP for matching. And in order to exploit Gaia, what you have to do is this. Internally, SCAMP has, it uses the detections it makes in the images, or that were source extractor made in the images, and it uses the astrometric reference sources on the sky. And by combining these two, it finds the ultimate or the final solution, astrometric solution. And there is what SCAMP calls astref underscore weight parameter, which assigns a weight, how much, whether the internal solutions should be weighted more or the reference solution should be weighted more, depending which ones are more reliable. And with Gaia, the reference sources are way more reliable because the accuracy is like on the level of micro arc seconds or milli arc seconds.
Compared to what you're centroiding on the image,
compared
right?
to what, you can maybe get a centroid down to tenths of a pixel or hundreds of a pixel if the source is bright, but certainly not less than that. So always the order of 5 to 10 milliarc seconds, but Gaia is better than this. So I found that usually the default is 1, meaning both the internal and the reference weights they're equally balanced. But I found that most data sets, if you use Gaia, they work much better if you give a lot more weight to the Gaia catalogs. Using this exposure loose setting. Anything else? No. So let's run that. That's also much quicker than the other setting in version 2.
Yeah.
So you get your scamp check plots. I guess you're familiar with them.
Yeah.
You just eyeball them. You always need to make sure that you look at if there's any scaling factor up here. So that's like 2 times 10 to minus 2 arc seconds. So that's
good.
A 20th of a pixel or something like that. So that's really good. And same also here for the relative astrometry, for the absolute astrometry. With Gaia, you always end up again on the order of a few milliarc seconds. And previously with the other reference catalogs, it was like 100 or 200 milliarc seconds. So it's much, much better now.
Crazy.
You should get a flat sausage, no wiggles or anything like that. If you do see wiggles, you might want to increase the distortion parameter a little bit.
Okay.
I can show you that in a second. That's a distortion pattern.
Nice.
Looks funny, but actually this is the real distortion. It's like this ring-shaped thing. Funny collimator in the white.
Now, if it's doing it separate for every image, is it somehow then stacking it as well, like for?
No, there I can't give you. I cannot answer that because the documentation of SCAMP is not sufficient enough.
Yeah, I know.
It doesn't. I do not know what exactly it does here. If it might be combining distortions from the various exposures, or it just shows you the first one, or I don't know.
Yeah.
And unfortunately, Manuel is so busy, he doesn't.
Yeah. I know it's hard.
He ignores my requests.
Yeah.
And well, that's the alignment on the sky, photometric residuals. And what you have to do is you either accept the solution or you reject it.
Okay.
So it looks good, you accept it. What happens then is that the
goes to the next filter.
No, you see, it already runs the next one.
Yeah.
Just eyeball them again, accept it. And then the third one. So when you accept the solution, what happens is it updates the FITS header with the zero order astrometric solution. So any shift and rotation is taken out. You can check that. You go into the memory viewer, you click on any image. Then up here you have these two buttons, source cut and ref cut. So
that's
by
cool.
source cut, can you see the green circles?
Yeah.
So this is what you detect in your image using your source extractor detection thresholds. And if you click on reference catalog, these are the Gaia sources that are used.
This is a really handy tool.
Thanks.
Image display, yeah.
I just hated it to do it manually before. I always had to open SkyCat or DS9 and load all the catalogs.
Yeah.
Like, and you can if you turn on this auto contrast, then you can quickly step through all the exposures and make sure that they're actually correct. But you would be able to, if your check plots are wrong, you would see already that one of the exposures is wrong, and this way you could identify which one it is. Yeah, you can also do that before you run the astrometry. Like after you downloaded the reference catalog, you would see a shift between the red squares and the green circles, and afterwards everything should be nicely together. If you go to the corners, you probably would, with the wide field image, I think in detector 3, you would still see a little offset.
Yeah, it's a pretty big
distortion the distortions are not corrected at this point. For that, you would need to resample the image, which is only happening at during the coaddition. Then sky subtraction. That's. Are you interested in diffuse H alpha light as well, or only in H2? Yes. Okay.
Yeah. So for this, I was using, just like you had in the previous version, just the grow factor for the mask. So I was doing like a big box of like 1024 pixels to model the sky, and then using the big grow factor.
You have to play with this. In this case, I mean, the options you have here are similar. So you can model the sky, which how big are your galaxies typically?
They are can be, an arc minute or so.
Okay, so nothing like.
It's not filling
comparable to the size of the detector. Oh,
yeah, like 1024 pixels pretty much would fit most of the galaxies inside of it.
1024. So that's 3, 4 or 5 arc minutes in case of the white film. Okay. Okay. Appreciable big. not negligibly
exactly.
small.
Like it's an issue. Yeah.
Okay. Yeah, then you could. Yeah, you could
I just made
try.
The kernel width.
Yeah, you could try this modeling and then use a suitably big mask expansion factor. You know what that does?
Yeah.
Yeah. Okay. I think between
I'm curious how you do it though, right? Because so you're not. So I guess I don't know exactly. I mean, I know the general idea, but I don't know exactly how you implemented that.
This is what I did was I re-implemented source extractor. Let me show you that. Source extractor computes an elliptic fit. Actually, it's not a fit, but it's a elliptic description of the isophone or the flux distribution using these CXX, CYY, CXY parameters. And using that, you can easily compute which pixels lie inside this ellipse and which ones are outside. This parameterization that's actually does not encompass the entire flux, but only about it's like a factor of 3 too small. That's why in version 2, I think you had to, if I remember correctly, if you enter the 3 for the mask expansion factor, this would be the minimum you want to give.
Okay.
I don't remember. A number smaller than 3 didn't make sense. So 6 would be 2 times as big as what the galaxy appears in the image, and 9 would be 3 times as big. So in the new version of Theli, I absorbed that. So if you enter 1 for the mask expansion factor, you would get roughly something that is as big as your brain would judge the galaxy to be.
Okay, like 3 in
twice
the old, right? 3.
Yeah, if you want twice as big, you just enter 2.
Okay. So you're just taking that whole ellipse and expanding the radius basically of it.
The factor 3 is already built in. You can try with that. The problem I see is if your target is fairly big, like in your case, if you make your detection thresholds low, and then use a mask expansion factor of 2 or 3, it can easily be that you mask half the detector or even more.
Yeah.
And then your sky subtraction is probably not very accurate. It depends. It depends on how uneven your background is, how big your galaxy is. If it sometimes they have a fairly bright center and a very diffuse but large extended disk, and whether you detect it in an individual image or not, then your mask might become too big or insufficiently small. It's you need to play with it, core at the image and look at it and decide does this still look reasonable or not.
Yeah, I was wondering actually how we know.
Yeah.
In reality, right? I mean, you'd have to compare it against some other measurement where you didn't subtract it, I guess, but.
Yeah, that's why if it's just for H2 regions, you don't care. H2 regions are compact. You just do your modeling and it'll be fine. But for diffuse, for diffuse extended flux, what I would recommend is you subtract the constant sky, which you can do on a detector by detector basis. And you can specify a specific sky area. So either you can say do it for each chip, which would be this option here. Then just computes the mode, the statistical mode, the most common pixel value after it has been masked. So that's pretty safe. Or if you have like very large extended objects and only one of the detectors sees the true sky background, you can say specify a sky area, then you click there and it will open this FITS browser, and then you select whatever image. This is the first chip that is a bit bad. You basically go there with your middle mouse button and you set apertures.
Oh, that's
and you
cool.
say those are the regions I want, which I think have a reliable sky estimate. And since the astrometry has been updated, it then looks up these coordinates across all your FITS files and does the measurements in there. It doesn't matter whether it's then falling in detector 1 or detector 2 or detector 3. So it's based on true sky coordinates.
Nice. Okay.
You just close it and then run your sky subtraction.
Okay.
In this case, let me just do a normal thing.
Yeah.
So yeah, because of this, I think once you separated your targets here, you can still create your source catalogs and do your astrometry and let it run for everything.
Right.
In one go. We can just try and hope for the best. Probably it will work for most of them. I'm pretty sure. Unless your source density in H-alpha is really low, then you might have a problem.
No, the SCAMP has been working pretty well for H-alpha, so I think it should be okay.
Okay, then you're good. But then for sky subtraction, this is something individual, because your observers might have placed the target in a slightly different position, maybe because they couldn't find a guide star, or the size and shape is different. So you want to fine tune your sky subtraction so you don't destroy any signal. So at this point, once you're done with the astrometry, I would go back to your data tree and then select only one target you want to work on.
So, I see, because otherwise it would do that average on a...
Otherwise it would apply the setting you do for the sky subtraction, it would apply them for all your targets, and it might not be
Oh, I
valid
see.
for all your
Okay.
targets.
So from each chip doesn't mean in every image look at each chip. It means for all the images find it for.
Yes.
Gotcha.
But if you do like that might be valid for some exposures, but it might not be valid for another target where your galaxy is very big and you cannot use the central chip.
Gotcha. Okay.
That would be over subtracted. Or your mask expansion factor might be valid for the source, the flux profile of one galaxy, but it might be too big or not big enough for another galaxy. So that you would then need to. I recommend you do that individually.
Yeah, I was thinking about. I mean,
like for diffuse flux.
Right. Yeah, it probably
tricky.
is best to subtract the mode now that I'm thinking about it, because in the end, then we're able to quantify the error that the sky subtraction is, or the variable sky is introducing, I guess, which probably is a better way to do it. Whereas if we do this, modeling the sky, it's really not clear what happened to the flux of our galaxy.
If you model, you will, if there is diffuse flux around the galaxy, you will destroy at least some part of it if you model it, for sure.
Yeah, in a way that's hard to quantify.
That's what it's supposed to do.
Yeah.
It's supposed to be like sky background, but not astrophysical flux. The two are very different, difficult to disentangle if your background is uneven. Yeah, so you could run this sky subtraction using this setting, using from each chip. I think that would probably give you a reasonable result if your galaxies fit within 1,000 by 1,000 pixels.
Yeah. Yeah, I think so too. There's nothing that's that big.
Then you have a reference set, and if then whichever target doesn't look good enough for you, you open a separate Theli session and work only on that specific data set, that specific directory.
Okay. There are some bright stars, I guess, that are potentially. I'm wondering because some programs don't actually really calculate a mode. They calculate some, approximate of a mode, but this is really doing mode.
What happens here? You mask all the sources you can find using these thresholds. That includes bright stars and the halos as well. And whatever is left, you build a histogram, and then I try to identify the peak of the histogram.
Okay.
So even if the star has some halo, if the halo is less than 20-30% of the area of the detector, you should still be able to identify the mode correctly.
Okay.
So the mode is fairly robust, but it the median would be biased already. So I'm using the mode, but
okay, and the expansion factor actually applies even for subtracting the constant sky. Okay, I'm not sure I realized that.
Yeah. Well, it would enlarge the masks around the objects, so it would make your constant sky estimate even more robust.
Yeah.
As long as you have a sufficient number of true sky pixels left, it will get the level correctly.
Right. Okay.
But in the end, your eye is the judge, or the best judge. You look at the coordinate image, you'll know immediately if it was correct or not. If any of the detectors is off, you will get a discrete jump in the background, which you see very clearly in the mosaic, the stacked image. So yeah, you could you could use this setting and run it on all your targets, and then whichever needs more improvement, you try and do it manually.
Right. Okay.
So instead of working on all the data, you just work on a subset.
Yeah.
Just to restore that, and then did I run it now? Yeah. Yeah, you get some estimate of the mode that is measured. This number that's also written in the also written in the fits header. Down here at the end, sky value.
Nice. Okay.
So you can trace that in the headers. Okay, for the coaddition, what you should do is for each target, provide the same RA and DEC for the coaddition. Because a coaddition, you observe a curved surface with a plane imager. The sky is curved because it's a sphere,
right.
and your detector is a plane, so you have some mapping. You have a projection going on or a deep projection.
Yeah.
And that projection needs a coordinate 0 point, which doesn't matter where in the field of view it is, but you have to provide one. If you don't provide one, SWARP will randomly compute it. No,
Okay.
not randomly. It'll take somewhere roughly anything near the center of the field of view and whatever way it computes that. But if you co-add, the coaddition happens independently of each other because it happens in this data directory and then in this one and then in this one. And your telescope pointing in the different filters will be slightly different. And therefore the coordinates that SWARP computes will be slightly different. So what you want is for your target NGC 1234, you enter the coordinates of that galaxy. As long as it's somewhere in the field of view, that's fine. The important thing is that it's the same, exactly the same set of coordinates for your on-band and off-band filter.
Okay.
And I'll tell you why in a second. You define the plate scale. Usually it takes the default plate scale. I think for the wide field image is 0.331.
Yeah.
The rest you can leave unchanged. Down here is a button, perform flux calibration. You can leave that on and then run it. So then you get the coordinate image. The wide field imager in Chile back then in 2001 had a problem that the baffle was too short. So there's a lot of scattered light in the background. Also this artifact that you can see here. And since I subtract the constant sky, you can still see that.
Right.
So that's why the coordinate image is always a very good judge, a good way for you to judge your sky subtraction in the data processing.
So would you leave it like this, or would you go and then model the sky?
In that case, I would not be satisfied with that. But that data is really, it has a lot of problems. It also has 10% 0 point variations across the field of view. It really depends on what your science is that you want to do.
Right.
So if you're only interested in high signal to noise things in the inner part of this PN, this planetary nebula, then you don't care. If you want to measure the radial flux profile, then you would be screwed.
Yeah.
And this data might not even be usable. So it really depends what you want to measure. But I would think this is ugly.
Yeah, that's kind of how it comes out with the INT if I don't do modeling sky too. There's a lot of structure
then
left.
you should ask yourself the question, what exactly is causing that? Is it maybe because I have still some saturated flat fields in my stack, which distort the relative intensities? So you should look at that. Or maybe your observer observed it against some cirrus clouds or in the wrong position of the sky. It can also be, I don't want to lie about this, but I've seen instruments where the gain has been unstable from on scales of hours. So
really?
You really see things changing all the time, and then of course it gets much harder to calibrate.
There was structure in, like you said, of sort of 0-point variations across the field of view. And so just comparing to like pan stars, let's say,
Yeah,
you definitely saw very strong residuals in the 0-point. So what I was doing was just fitting like on your suggestions, fitting a 2D polynomial to that and trying to flatten the 0-point.
To the coordinate image.
Yeah. To the co-edit image.
That's what I would have done too. Or what I would do in your position. Yeah. What you get when you you hook off this perform flux calibration, if you do that, you get this additional window here where you can compare against pan stars, for example. So that was B-band filter. Pan stars doesn't have B-band, but if you want to do that, you could pick the closest thing, which is G.
Yep.
Some color term. Run that.
And it knows the linearity limit from the instrument setup file?
You provided the saturation. It knows from the data, but your nonlinearity might be 10 or 20% lower than this.
Yeah.
That depends on the instrument. So you can say, I don't want to use any sources that are brighter than 1,000 electrons per second in the coordinate image. Then these sources won't be used. So you get to decide.
Yeah.
And here's a usual aperture growth curve. You pick your sweet spot. You can click on the data point, and then it computes the 0 point and the color term with respect to the pan stars photometric system. And those are then the sources that are used.
And does that go into the co-ed header?
This is copied into the coordinate header.
Okay.
And yeah, it's copied into the coordinate header. So you have all that information there.
Perfect.
The magnitude system is converted to AB mag.
Yeah.
If your reference catalog is not. You also get the conversion factor to Microchansky if you want the absolute fluxes.
That's amazing.
Yeah. About this plot, sometimes this works really well if you have a sufficient number of stars. And sometimes with pan stars, what I see is like there's another cloud of data points up here, which I haven't analyzed where this is coming from. I suspect either that's galaxies and the magnitudes I'm measuring are not really accurate, or the pan stars photometry is a bit dodgy. I'm still linking. Yeah, this is still pan stars data release 1. It's actually pretty old right now. There's data release 3, but that's not accessible to the world. Data release 2 is, but it's not available yet by the CDS server in Strasbourg, which I'm interfacing. And the pan stars DR2, which is on their database, I found it somehow. I just didn't have time to implement it because pan stars has this interface and SkyMapper has this, and the Vista survey has another interface. it's so much easier if everything is in CDS in Strasbourg, then it's the
Yes,
same
yeah, for
interface.
sure.
So
Right.
eventually, but I know that the photometry for Penstars DR1, sometimes it just doesn't add up.
But those are getting rejected, it looks like anyway, right?
Yeah,
Or
but
does it throw off the
sometimes
point?
the cloud is so broad that the fit doesn't converge
Mm,
to the correct solution. So what you
okay.
can then do is you can increase the detection threshold, so you keep only brighter sources.
Okay.
And then maybe the spurious galaxies they go away. We can try with 30.
So I'm doing something similar. I have a program I wrote to do the same thing compared to Pan-STARRS, but and I was doing it for H-alpha too, which I think is okay, right? I mean,
that's fine.
Yeah, because you just go into an AV system, right?
Yeah, exactly.
Yeah.
They could do that.
Okay, cool.
Just then you know how to scale your
right, exactly.
on-band and your off-band image.
Yeah.
So now with higher detection threshold, then you see all these other detections that disappeared. So they start to pick up a second. Yeah. What I wanted to do is to provide a functionality that you click on these data points, and then it shows you which sources they are in the coded image. But for some reason, the indexing doesn't work. I cannot identify which data point this is by clicking on it.
Oh, that's interesting.
I talked to the guy who developed this this module that I'm using, but he hasn't replied yet. By the way, you can zoom the axis by scrolling here or scrolling there, or you can just by clicking you can shift it.
That's really nice.
And you can show the reference sources that were used. If you click this button here, then you need to zoom in. So all the ones that are yellow that are used to compute the 0 point, and the ones which are red are not detected because I used a very high threshold here. So
right, okay.
You get some visual feedback whether this makes sense or not.
Yeah. And what are you measuring is using source extractor to measure the fluxes?
I used my own implementation of source extractor. So it's the same numerical, it's the same formalism, so to speak. But by implementing it myself, it's much faster.
Oh,
the sky, it's measured the sky. Actually, I think my background measurement is better than in source extractor because it's source extractor runs only once.
Yep.
And whereas I'm iterating, I detect my sources, I compute the background, I subtract the background, I detect the sources again, I repeat that twice.
Okay, but not like a uniform. So you're doing some local subtraction of the background. I'm just worried, like thinking of all the variation that you're seeing in the sky there.
It's a it's not a fit. It's a local. It's
it does a local estimate.
It's a smoothed version of the local sky.
Okay.
I think I'm doing 3 iterations. So it doesn't. Sometimes source extractor is the problem that towards the edge it runs off. It overestimates or underestimates the sky. So this is not happening here.
Okay.
So for source photometry, I think you get a pretty accurate local background.
Okay.
And then it's just the aperture, the typical growth curve that you've seen. You pick the sweet spot. It's running. Actually, it doesn't start co-adding the next one until you've done the photometric 0 point. So, but in principle, I could just let it run.
Yeah.
I could probably fix that. So it just runs through everything.
So from sky subtraction to co-addition, I should do each object separately. Like each target, right? Do the R and H alpha together.
Between astrometry and sky subtraction. Up to astrometry, you can do everything in one go.
Yeah.
And then you should break it up.
Okay.
Well, if you just do the mode for each chip, you can just run the whole thing automatically.
Mm-hmm.
But if you want to manually fine-tune the sky subtraction, you should, once you're done processing everything, you should pick out that specific target.
Right. Okay.
In its 3 filters and set up a new Theli session, just providing the science directory to these 3 filters and then run the sky subtraction.
Right.
And
Okay.
iterate until you're happy. Yeah, one thing I still wanted to tell you about the coordinates.
Oh, yes.
So once you've done the coordination in your 3 filters, you can go here on this stack of red, green, blue layers. You'll only have 2 filters. In this case, I have 3. So you select all the filters of your target. You click on crop quoted images. And what it does is it identifies the largest common area to both of your filters. And it crops this area. So you have then the same source appearing on exactly the same pixel.
And that's after you set the reference, right? You have to have the same reference RA index for all those.
For that, you need identical RA index. If you don't do that, it cannot identify the correct mapping. And so once you've done that, then you find this color _ Theli directory. You can go in there, and then you have your _ cropped image in the B filter and the R filter and the V filter. If you do that. You see that they have the same reference pixel. Well, actually, RA tech is different. Why is that?
Because I don't think you said it. You didn't set it.
Oh, I didn't provide.
Yeah.
Okay. Yeah. Okay. So in that case, it didn't work.
Yeah.
Yeah. I was thinking. Okay. Yeah, you would need to provide that, and then these images would be perfectly registered, and you can do your sky subtract your difference imaging basically using them after adjusting for the flux scaling.
Right. Perfect. That's right. So co-edition, I do have to do one target at a time because there's no way to feed in a bunch of RA and DEC, is there, for the reference images if you're stacking them? You know what I mean? If I was doing like 3 targets at once.
Oh, I see what you mean. No, that would not be possible. Yeah. What you could do is that's what I was just thinking. You could create a directory, which I usually call all if I have several filters, and then you copy all the fits images from your on band and off band into this one. Then run your you would also need to copy the headers, and then if you create a coaddition, it detects that you have 2 or 3 different filters in the same directory, and then it asks you, do you want separate coadditions for each of the filters, or do you want all the filters quoted into a single image? if you want a very deep image, for example.
Mm-hmm.
And then you're also asked if you want identical coordinates for all of them, or whether it should do it independently. But then you're at this point, you're already down to a manual level, and you need to fiddle with the interface. So
Yeah,
I would yeah, at that point, I think there's no way around that. You have to break it up and do it manually. But at least until the astrometry, you can do everything in one go.
Yeah, which is,
or even the sky subtraction. So somewhere at the end, there's a breakpoint where you have to leave the automated processing and do it in a manual fashion. Then.
Okay, got it. So what is it getting actually from the instrument configuration file, when you're selecting a particular instrument?
Not much.
Okay.
There's previously everything was in this configuration file. I don't know where. There we go. But it's just the instrument name or an abbreviation, which would be then the string here in your file name. The number of detectors, some geographic things for air mass calculation if it's not present, a plate scale if it's not present in the FITS header, the gain value if it's not present in the FITS header, and some overscan regions and data sections. Most of that is now updated internally, so I'm not really actually relying anymore on this.
Okay.
The old version did. In the new version, I tried to read everything from the FITS header, and if the information is not in the FITS header, then it falls back onto this configuration file.
Okay.
In the rare cases, it can be, or if then though there's a mismatch between what is encoded here in this file and in the data, there can be a conflict at some point when it comes to masking unilluminated areas, and I'm catching that. So you get an error message then telling you that there's a mismatch between your data and this configuration file, but that should not happen with anything that is pre-configured, something you can select in this list.
Okay.
Yeah,
because we potentially, if we're allowed to observe in the spring, we'll be getting data from what is it called? There's at the Bach telescope on Kip Peak. There's the 90 prime camera.
Just send me a raw file and I'll set it up for you.
Oh, okay. Perfect. Because this would be a lot easier to do.
It takes me 10 minutes and it saves you probably hours. So it's really easy, but I just need to do that myself.
Okay.
And then other people can use it. So
perfect.
Just the best would be a raw science exposure from some target on sky, where you can see
that has
as it comes from a telescope,
right,
which has everything. So I can see the overscan, the complete structure of the FITS header, and also whether it comes in a multi-extension FITS format or whether the detectors have different readout channels that need to be pasted together and so on.
Okay. All right. Sounds good. Well, thank you so much. This was super useful.
You're welcome.
Yeah, and I can. I would imagine this video would be useful for other people. I don't know how many emails you get typically on asking for help, but
Not so many because I haven't advertised it very widely yet.
Oh, okay. Okay.
So I only have like 20% of my time to work on this. Actually, it's much less at the moment over the last year.